Okay, before we start, let me ask you, who hasn't started trying the simulation? Okay. Can I trust that rest of you already finished the simulation? Okay. Who has the issues accessing the servers? Oh, sorry? Okay. Do you have still issues with the accessing the servers? More secure, okay. Okay. So in the worst case, what you can do is that the EITU, we had the training session, it's open actually 24/7. In the worst case, you can actually do it there as well. But of course, my preference is that you try accessing from your home.
No problem. But I think on Sunday it's not open 24 hours.
Oh,
Yeah.
okay. Thank you for
Sorry?
Sundays.
Yeah, and Saturday is also not like they were. I think after 6 p.m. you have to leave or something.
Let me check with the EITU folks. Yeah. But anyways, I think preference is that you should access from your laptop so you can do it from your home. But if you need a bigger screen or you need stable connection, you can also go to the EITU. Okay. Who has tried 3.3? Already asked you to do so. Okay, who hasn't done it yet? Okay. Then I think I have to go through this again because, as I said, this CAT session will really help you doing the project number 1. And so far, it's something that you can manage, even if you haven't done it so far. But unlike other modules, if you really postpone the contents coverage on yourself until the last moment, I can tell you this module will be very difficult. But if you do it one by one, weekly or weekly, with the request that I'm making, such as the simulation, you do it on time, you will manage it. Okay, anyways, let's start. So 3.3 is asking, redesign the common source amplifier in example 3.2 using a current mirror biased common source as load. So basically, I place the PMOS and MOS here, and this is the example 3.2. But you can see that we use PMOS as a load, but we want to get rid of this voltage source that biases the PMOS DB. Again, if you look at it, what this bias voltage is doing is to make sure that PMOS is in saturation. And why in saturation we already know now that you want to make sure MOSFET is in the saturation region so that the DC resistance is low and then AC resistance is very high. So that's what the DB is doing. And at that moment, we want to achieve the gain of over 40. But anyway, the metrics given was the same as the 3.2. So we want to redesign this. How I did it was to replace the PMOS only with the PMOS current source. And if you recall what we discussed last week, what does this PMOS do? Can you give us some insights? If you compare the left and the right we can see that we have one additional PMOS, and the rest is similar, if not the same. So what does this PMOS do? Why do we bother adding one more PMOS here? Each two mirror current, yes, that's correct. And mirror which current to where? One source, yes. Two to the PMOS over here. And is that current the same as the NMOS current in the biasing? Is that current that you copy the same current that will be flowing through the mirror, right? That's right. So that's the current mirror. But why? Why do we have to mirror it? Why not just go ahead with this? Which is, that's correct, and which is, why do you want to avoid it, you know? Correct, correct. So thank you so much. So what he said was, this was to avoid using multiple voltage sources, multiple DC voltage source. And on chip wise, you have one battery source. So you want to use DC-DC converters, the voltage regulators and DC-DC converters to generate the voltage when you need. And the little DC source you have, the little panic, little headache you will have. So your goal here is to reduce the number of DC sources that you're going to use. How to do it is to just increase the current source with the current mirror, like this, as an active gate. That's how it's achieved. And then you may be asking, how do we make this current source then? Isn't it that just we convert a DC voltage source to current source? So you might be looking into that way. But simply speaking, most of the time we use DC and just a resistor, passive resistor as a current source. Because this is a DC source, we don't have to worry about the resistance difference between the AC and DC. So we just use a DC source here, DC resistance, and that biases everything. Okay. By doing so, we achieve the gain of 40.25, the voltage swing 1.5 briefly, which is shown here. Any questions? I really ask you, I think this week is the deadline for you to make sure that you simulate the examples. And if you face any issue with the CAD tools, or connections, or etc., probably you need to clarify it this week. Because starting from next week, the speed of discovery should be faster. And also the content you'll be absorbing has to be really well absorbed for the first 4 weeks up to now, and for the first 5 weeks. And then afterwards, we'll be building the house upon the knowledge, the books that we learned from week 1 to 5. Yes?
I want to know what's the name of the component shown on the V-out.
The V out, you mean this one? I mean here?
Yes, what's the component?
This one.
Yes.
Yeah, this is not a must. We call it, this is the floating node, right? We just label it. For your simulation, you can just use the pin. Remember the pin that we had in the CAD training session? The output pin. If you press P, it pops up with a pin and you can just place it there. Or if you go to the left, there is a floating node, which just shows that if you have a floating node and then just add it there, it will just show this is a node that you're not connecting anything else.
So the cadence of this data function, I don't know what's the
That's right, it's called no connect. No connect. But as I said, please try using the pin, the output pin, because for this amplifier, you'll have input and output, right? It's better you do it that way. And if I were you, probably after the project number 1, this is not required, not a must. I would just create a symbol with a triangle with the OPM, with input and output. And in order to create the symbol, you know that you have to have an input pin and output pin. Right? Any questions? Yes?
How can you see from that simulation that this swing is 1.4?
Oh, okay, it's not visible here. There are some small tips. You can actually use your eye to track where it is, or if you want to make it very accurate, place your mouse cursor or the pointer near here, and then press A. They will tell you the point. Then a small guideline pops up and shows the exact voltage number. And then if you go to the other end and then press B, A and B points, you will exactly show the delta in time as well as the voltage.
So, but plus part of the string. And
So for example, here each around I see around 1.0, and downside is about yeah. Then you can just measure it. Each like 0.9 here to 1.1. So you can measure it with the A and B. So it's in the waveform window. Go to the waveform window, and then place where you want to point it, measure, like probing with the oscilloscope, and then press A in the keyboard. It'll pop up the exact number in the voltage. All right. Okay. Any questions so far? Okay. There's strange silence. Okay. First of all, before I go on to this page, there are many things that you will encounter in the real design problems that you will encounter that you didn't see in the textbook. And one of such is as follows. This is the load. Let's say one of the load is a speaker. You're trying to drive a speaker here. And then this amplifier has a gain of 100. Your sine wave input was 10 millivolts peak to peak. And how much voltage swing do you expect if it's 10 millivolts peak to peak? Is this a stupid question? 1 volt peak to peak, right? 1000 millivolts. Except for those who took EE447, you already know the answer, so please don't answer those who already took PS4. What would be the voltage if you actually probe here with the oscilloscope? Will it be 1000 millivolts peak to peak? I know you took the course, so you shouldn't answer, please. How about you? Can you expect, is this 1000 millivolts? Oh yeah, maybe you can answer, yeah. Yeah, be proactive, you can answer. It can be wrong, don't worry. You're sitting in the lab right now.
Oh, okay.
This is just the lab.
The amplifier.
Amplifier has gain of 100. Input is 10 millivolts peak to peak sine wave. Okay, you probe with your oscilloscope, you attach the speaker over here. Okay, if you're accurate enough, you might be saying, okay, we cannot know the answer unless we have the resistance of the speaker. But let's make it common sense. The speakers typically have the impedance of around 4 to 8 ohms, if not 16 ohms, if it is earphone. Let's say 8 ohms. Any thoughts?
I remember in the radio frequency, I did a match network to satisfy that.
Right. So you're getting close. Okay, typical output impedance of an amplifier, right? That highly depends on what type of amplifier we're talking about. But the voltage amplifier that we have learned so far, like the common source amplifier, will have the output impedance of around, let's say, if not hundreds of ohms, sometimes kilo ohms, if not tens of kilo ohms. Let's say 1 kilo ohm, just a simple problem. That means you will have a series impedance of 1 kilo ohm looking into the output port. Do you remember that, if you look at the output over here, the AC resistance was something like 3 kilo ohms, DC resistance was about 200 kilo ohms. That 3 kilo ohm means that if you look into the output port, signal-wise you will see 3 kilo ohms. But just to simplify, let's say it's 1 kilo ohm here. Can you now see the problem? If you don't see it, let me remap this into two. Multiply by 100 over here. without this connection, yes, you will be seeing 1000 millivolt because you have amplified with 100x. But the moment you connect this, what happens? The 1000 millivolt outputting from this amplifier is divided. Can you see that? It's a voltage divider. 1 kilo ohm versus 0.08 kilo ohm. Engineering tolerance, I said anything below 10% is error, right? You will see practically zero output. Of course, if you say it accurately, it will be 1000 plus 8 dividing 8. So that's what you'll be seeing, around 1 millivolt or less. Okay, so you have 10 millivolt peak to peak with 100x gain, but resulting is 1 millivolt peak to peak or less. What's going on here? Is this actually functioning as an amplifier? Right. Can you see the problem? Yeah, what do we call this? There's terminology we call this. Okay, looks like you partially know the answer.
Impedance mismatch.
It's a mismatch in impedance, yes, but the term that we call with the load over here, this happens when the output impedance of an amplifier is too high compared to the load, or consequently the load impedance is too low compared to the output impedance. We call it loading effect. Okay. Same problem happens, exact same problem happens if the source impedance is too high and the input impedance of amplifier is too low. Can you see the problem as well? So if this was the loading effect, actually terminology is into the input side, but same term can be used for the output side. If the output impedance of the source was, let's say, 1 kilo ohm, and then the input impedance of this amplifier was only 8 ohms, then the same problem happens. The output impedance dividing the voltage with the 8 ohm will be shown on the input of the amplifier. Although the input signal was 10 millivolt peak to peak, only a small fraction of it will be coupled to the input. We call it loading effect. Just to summarize, this problem happens if the source impedance is too low. Source impedance is too high, source, and then destination load. Impedance is too low. Then this problem happens. For a voltage amplifier, you want exactly the opposite. You want to have the source that is delivering the source, the signal, the impedance of that to be as low as possible, and then the load that you're accepting the signal has to be as high as possible. Let's look at the other way around, right? Let us assume the source impedance of output impedance of the amplifier is 8 ohms. And then you have a load which is 1 kilo. Then what will be the voltage over here? Can you guess?
1 volt peak to peak.
It should be 1 volt peak to peak, right? Can you see the problem? And can you see the solution now? Right? So, okay, are you sure that everyone understood the problem? Did you understand? Kind of? Okay. Can you see that if the output impedance of an amplifier is too high compared to the load, then the output will be divided between these two impedances. Can you see that? If the output impedance is the same as the load, which power amplifiers prefer doing that for maximum power transfer, then you will have the output of 1 volt, which should be divided equally, half and half. Now, if the load is too low in impedance, now the output that goes to the load is smaller than that is in the output of this amplifier. In the extreme case is a speaker. Speaker has very low impedance. So it means that you need to have a specialized buffer. Specialized buffer in circuit to drive a low impedance load. So if you understood up to here correctly, let me ask you a question. What should be the characteristic of this buffer in terms of the output impedance? Should it be low or high? Can you guess? Low. Okay. Who thinks the output impedance of this buffer should be low if the load is low impedance? Okay, I see around more than half. Who thinks it should be high, the output impedance? Hello? Hello? I haven't seen you raising your hand. So do you think it's neither?
Sorry, I was looking at something.
Okay, what about you?
Low.
Low. And you?
Low.
Yeah. Oh, you didn't answer it? Do you think the output, let me repeat the question. You are trying to drive a load which is a low resistance. Should the output of the buffer that you inserted, output impedance, is it going to be low or is it going to be high? It's your right if it's wrong answer. Can you guess? You don't want to? Okay, never mind. I will ask you later. How about you? Yes. Same. Same. Same means they should be the same.
Yeah.
Okay. That is correct for power amplifiers. So if your goal is to deliver maximum power, you need to have the same impedance. For the voltage transfer, you have seen this problem. For the maximum voltage transfer, you need to minimize the source impedance. You want to maximize the load impedance. So that said, if you were to add an amplifier here as a buffer, you want to have as low input impedance as possible, preferably zero. And load impedance, input impedance has to be as high as possible, and then the output impedance seen from here should be as low as possible. So the output impedance is so low that even with the 8 ohm, the voltage division, you will still have most of the signal being passed. So the ideal buffer should have input impedance infinite, and then output impedance low 0. That's the ideal voltage buffer. Okay, any questions up to this point?
So for the buffer, there should be one resistance and input and one at the output.
So this input impedance that I shown as a resistance is not an actual resistance, but I'm just replicating as a symbol. That if you look into that port, you will be seeing equivalent resistance. That is shown as reflected as a symbol here. And for that input impedance for voltage buffer, it should be as high as possible. So even with very high impedance source being connected, input that you'll be dividing with the input impedance of the source is even higher. Right? So then let's say if it is infinite impedance, it doesn't matter what kind of output impedance of the source it may be, you still have most of the signal pass through the buffer. Right? So if you look at it, this is the problem. You have a source impedance that is dividing the voltage with the input of the buffer, voltage amplifier. And the problem happens if Ri here is too small because you can see that it divides the source voltage. Right? Same problem happens at the output. If the output impedance of the voltage amplifier is too high compared to the load, then this R naught and the load resistance will divide the voltage after amplification. So that was the problem I showed over here. If the output impedance is too high of the amplifier and compared to the load, even after good amplification, most of the amplified signal will be eaten by this R naught, not to the load. Alright? So how do you solve this issue? This issue, if you understood what I'm talking about, this equation is just replicating what I'm saying. Please do not try to memorize this. Just intuitively look at what's going to happen if you have the output impedance too high compared to the load. So what you'll be doing in this case is to add a buffer. What's the role of this buffer? The problem happens if the output impedance is too high and the load impedance is too low. So your role of the buffer is at the presence of very high output impedance of a voltage amplifier, your input impedance is even higher. So even with that high impedance of the output of the voltage amplifier, most of the signal will be shown reflected in the input impedance of that buffer. And consequently, the output of this buffer impedance shown over here from the port of the buffer is very, very low such way that even with the low resistance value in the load, you still have most of the signal being passed to the output. I summarize, input of this buffer should be as high as possible. The output of this load has to be as low as possible. Can you see that? Okay. Who didn't understand yet? Okay, for the time being, I will think that you all got it correctly. So if I reflect this into the voltage divider, this is how it works. You have the gain of the buffer, gain of the amplifier AB. That is multiplied by the voltage division of the input resistance and the output resistance, which is dividing the input resistance value. If you have very, very high input impedance, very high value divided by very high will be almost 1. So most of the signal will be passed to the buffer. And if you look at the other way around here, voltage division of OB, R naught B, and then our load will be load divided by R naught B plus R L. If you have the output resistance of this buffer very, very low, then RL divided by RL will be again near 1. Alright? So this is what we are going to do. An ideal buffer has the following characteristic: input from its division to gain will be 1, its output resistance will be 0. So thus for the ideal buffer, amplifier's output has no loading effect is happening. So this is why we need an amplifier of gain of 1. The buffer typically has gain of 1 or less. But at the same time, the input impedance is extremely high and the output impedance is so low. That's the characteristic of the voltage buffer. Okay? Is that clear? Alright, very good. And the source follower has such a characteristic, all of it. High input impedance and low output impedance. So we'll look into that. Okay, so this is a source follower. Again, new type of amplifier shown with the transistor. Your first job is to not panicking. Right? So let's look at this transistor here. Now if you look at it, typically the amplifier you saw so far, we were taking the output from the drain of the transistor. Here now you have the gate, which is coupling the input. And then the output is taken out from the source, not from the drain. While it looks very similar to taking out from the drain, the result is dramatic. It's very, very different. So now you typically have a source resistor, which is RS. And if you look at the voltage at the RS point, this voltage is clearly non-zero. Why? If there's bias current flowing, RS multiplied by current will have some, it will exhibit some voltage over here. And source voltage is non-zero. And the body will be connected to the lowest potential, which is ground. So the body bias and the source bias is different. And what's that condition called? What's that inducing? That's where the body effect happens. Do you remember the body effect? Right? Body effect, if you recall what it was, let's give a recap. If the body bias compared to source is higher than the body in the source, then the threshold voltage actually decreases. If the body bias with respect to the source is decreased, then the threshold voltage increases. That was the body effect, right? And as you can see here, the common source amplifier without the source impedance doesn't have the body effect because source is connected to ground, body is connected to ground. But here, however, because the source impedance is different, I mean source voltage is different from that of the body bias, you will see the body effect. What does that mean? Small signal model has the backgate effect. It has a small, around typically the eta of 0.2 to 0.3 I already mentioned, has a small difference conductance that is happening from the body effect, and there's R naught, which is shown. But we are not taking the output typically we are taking from the drain side, but we are taking out from the source side. And the drain side, if you look at it from the AC point of view, it's AC ground because it doesn't change over time. And the source is also connected to ground. Alright? So in this case, okay, you will set up the equation. I'm just showing you the equation to explain how it goes, but I ask you not to memorize this equation unless you actually understood it, and it's not necessary to memorize it. So if you look at how this works, the output voltage divided by the RS and divided by the R0, that will be the current. It's the same as the transconductance VGS GM1 minus VE minus V out minus the body effect factor, where the VBS is actually minus the V out, right? And in that sense, the AV, which is the gain of this amplifier, will be GM1 divided by GM1 plus GMV1. GMV1 is typically around 10 to 30% of GM, plus 1 over RS plus 1 over R0. And clearly, these are positive values. So you can see that Gm divided by a bigger value is less than 1. Which shows the gain of this common drain amplifier or source follower is actually less than 1. So if you just present this without this context, you might be asking, why do we make an amplifier that has gain of less than 1? Isn't the amplifier supposed to have higher gain? The answer to this is because, we will learn it, is that the input impedance of the source source follower is very, very high, and the output impedance is very low. That's exactly what we need as a voltage buffer. Alright? So, if you look at it, just go here. If the R01 from here, if R01 is very, very high compared to the RS1, then you can get rid of R01. Then the output, the voltage gain will be something like this. If the GM1 is very, very high compared to the RS, 1 over RS and 1 over R01, which is typically the case for voltage buffer, then the gain of this voltage buffer will be near 1. So if I were to design it, typically based on my experience, the voltage gain of the source follower is typically about 0.7 to around 1. That's the ballpark you want to see. Alright, any questions? Okay, do you now understand why we need an amplifier that has less than gain of 1, but input impedance is very high and the output impedance is low? Okay, any questions up to here? Okay, you might be asking, and now you know the drill here, I don't like this force resistance. Why? Why? Can anyone tell me why I don't like that source impedance and passive resistance? Yes?
It has a high DC resistance or a low AC resistance.
That's right. How do you, in order to have a gain of nearly 1, you need to increase the transconductance. Transconductance increase means more bias current. More bias current means elevated voltage over here. Ideally speaking, your bias point should be half of VDD to allow for half VDD swing, the full swing, right? But if you increase the transconductance, the DC level increases, then it reduces the allowable swing, right? So then, that's not good. And the exact same problem we have with the common source amplifier. How do we solve it? Okay, can you give us some insight? Excuse me. Yeah, the question is, the RS over here, if you have this passive resistance here, the DC bias point, as more current flows will increase, that reduces the effective swing that is allowed. And same kind of problem we've already learned from previous lectures about the common source amplifier. How did you resolve that problem, the headroom problem? Do you remember? You don't remember, okay, that's fine. But do you see the problem here? Let me repeat it here. Do you see the problem that in order to, from here, the gain over here, in order to have a gain of nearly 1, you need to increase Gm, which is the transconductance. If you increase the transconductance, that means you can flow more DC current, more current here. If you flow more current, you multiply that by the resistance here, the voltage here increases, right? Ideally, the output should be biased at half of VDD, so then you have around half of VDD to the other side and half of VDD to the up, so the maximum swing is there. But if you start increasing the DC bias, you have smaller room to play with in the upper side, right? That's the same problem we had, the opposite problem we had with the common source amplifier. The answer is, we use the active source. Instead of a passive resistor, we added the transistor that operates into saturation. Right? And in this condition over here is they need to make sure the NMOS here is actually in a saturation region. So that the AC resistance is very high. In other words, the swing, the voltage swing you'll be seeing, the resistance R02 is very, very high. But the DC resistance is not that high. Right? That's what we did as a voltage source. I mean, active load, so to speak. And in this case, voltage gain is simply replacing the RS with the R02 because you're looking into the R02 terminal here. So then instead of RS, it's 1 over R02. And R over R02 and R01, as you know, for AC signal is very high. So you can approximate that by GM1 divided by GM1 plus GMB1, where GMB1 is typically 10 to 20% of M1. So it's nearly 1. It's not exactly 1, but it's much better. Okay? Does that make sense? Now, in this case, the output resistance is, of course, the RS1 source, the impedance from the source side, in parallel with the R02. So, what the message I want to give you here is, after I explain this, by just looking into this schematic here, without drawing any equations or any equivalent circuit model, you should be able to know what is the output impedance, roughly. From here, let's do the training. From the output port, you see the source port, which is RS1, and then you see the drain of M2, which is R02. Both are connected to the AC ground, so RS1 in parallel with R02 is the output impedance of this common drain amplifier. Alright? What about the input impedance? If you couple to the input over here, what do you see? You are trying to flow water in. What do you see? You see a barrier. No current flows in, right? That means the input impedance is very, very high, right? DC impedance to the input is nearly infinite. Of course, in the real CMOS, it's not infinite, but it's very high. Even the AC signal will be fairly high, so that you can already see. So there we go, we achieve the goal of having high input impedance and low output impedance. So for the output impedance, how much is it? RS1 in parallel with R02 will be, if you look at it, it's 1 over GM1. Because Fi is around 0.2 to 0.1, I just approximate that to be 1 over GM1, which is small enough. Right? And for RS1 in parallel with RS, which is the passive resistance case in the previous slide, it's same as 1 over 1 plus Fi with the GM1. But the problem with this case is if you increase the GM to lower the output impedance even further, now the biasing with the limited swing problem happens. That's why you prefer using source follower with the active load. Okay? Alright. Just to give you some update, today we'll have many equations. But the goal of today's lecture is not for you to memorize the equation, as I always say. What I want you to do after today's lecture is by looking to the schematic without drawing the equation, you know that, okay, output impedance is RS1 in parallel with R02. That's it. If you can identify what will be the output impedance, what will be the rough gain, without drawing the AC circuit equivalent model, without drawing the equation, that's the goal of today's lecture, alright? And actually, it requires some training. Okay, similar to the common source amplifier, M2 as a common source, current source as a load provides high AC input impedance and low DC impedance, which solves the output swing issue. Okay. Okay, so far we have learned about common source amplifier. Common source amplifier means something that we've already learned. Your input is coming from here. Input is the voltage difference between gate to the source. Output is from drain to source. So from input to the output, common port is the source. That's why it's called common source amplifier. Common source amplifier is for high gain, right? Common drain amplifier, you just like voltage forward has the load here, and then it's the out. You have the input and the output. The common port is the drain. That's why it's called common drain or voltage forward. The goal here is to have high input impedance and low output impedance. Now the third one is the common gate amplifier. We call it a CG amplifier. Here now the VB is connected to DC bias to make sure N1 is in saturation. And you have the source input coupled to the source of the transistor, which is quite strange. You have the input from the source, and the output is from drain. Great, this is called a common gate amplifiers. I'll come back to the frequency response later. But this is, we are going to look at what is the gain of this amplifier, input impedance of this amplifier, as well as the output impedance. Alright? Just to give you a peek of what the result will be, gain of this amplifier will be very similar to that of the common source amplifier. So it has to be related to the transconductance of the N1 multiplied by the RD. If you remember the common source amplifier, the gain was transconductance multiplied by the RD. Right? Remember that? Are you sure you remember that? If you don't remember, we have to go back and check it. But anyways, okay, so here we have the R01, R prime not 1, which I'll be looking at as output impedance, looking into the drain of the N1. But because of the presence of the RS, the R01 will be slightly different from typical R0 that we have seen, which is going to be higher. And the source resistance seen from the source port will be RS. If you draw the equivalent circuit, which is over here, you will see the source impedance reflected over here with the RS1, which is looking into the source of the transistor. And then the output R0 prime 1, shown as here, reflected over here, and then RD input to ground. Again, this type of equivalent circuit, I prefer you not draw this for the final exam or for your design. It's not going to help. This is just for understanding how we get to the conclusion. Alright? So we need to find, for this case, we first need to find this black box, which has the GN1. So instead of the transconductance over here, we will just look at this black box as the transconductance, and the RS1 and R01. Those are the metrics we want to figure out. How do you do that? We do it by the following. We'll do some trick here. We are going to draw the AC equivalent circuit like here. It's the same over here. We have the RS1 and R01. And remember, because of the elevator, the same problem as we saw in the common drain amplifier, the source impedance, because of the presence of the RS, the source voltage is not zero, whereas the body of N1 is zero, which implies there will be body effect. If there's a body effect, this new small F8 transconductance is present, right? So we will put that in here, and if you set up the equation for across this node, you will be seeing, I just did it for you, this for you. You will have the source impedance to be R01 plus RD divided by 1 plus the transconductance combined multiplied by R01. And the R01 prime, which should be looking through the drain port, looks like this. R0 prime 1 will be 1 plus GM, these two backgate and then the transconductance combined, multiplied by the RS, multiplied by R0. Okay, how did we get this? From this equivalent circuit, alright? And how do you know this? I mean, what's the implication of this? Is that if you didn't have this RS, just like in a common source amplifier, the resistance seen from the drain port would be R0. But if you have the RS on the source of an amplifier, that RS will be multiplied by the transconductance, and then transconductance multiplied by the RS will be multiplied to the typical R0 we already saw, which implies this R01 compared to the R01, the R0 prime will be much higher because you have this GM multiplied by the RS, additionally multiplied by R0. Alright, I repeat, you have the source impedance attached to the source. Then if you look at the output impedance from the output port, that resistance value will be multiplied by the transconductance, then multiplied additionally to the R0. right? So the output impedance seen from this port will be extremely high. Okay, let us put this aside for now and try to find the GM. Now the GM will be the transconductance of this battery comparing, including the source resistance values. So we need to find out drain current in AC signal wise. And for this, we are going to transfer this M1 into this equivalent AC model. You have the voltage dependent current source with the R1. And then the drain current will be this direction, flowing into the drain. Right? And here, this voltage dependent current source, again have to consider the backgate transconductance. And, I will solve this equation for you. Again, you don't have to memorize this. The transconductance is defined as the current divided by the voltage, right? G inverse of the resistance value, as we have to do that. So in order to know that, we need to know the IE, drain current. And drain current was induced from here, which I already did it for you. And you're dividing that by input. The resulting transconductance will be GM1 plus GMB1, which is backgate transconductance, plus 1 over R01. Okay, that's the overall transconductance, which with the R01 typically very high, 400K or over, you can just ignore this third portion. So the remainder is just GM plus GMB1. Okay, I know it's a bit puzzling, but why did we get this transconductance? Why were we trying to find the transconductance? It is because we want to know the gain. And what is the gain? This overall transconductance multiplied by the RD. And one of the transconductance is GM plus GMB1. And that's exactly the same as common source amplifier with the body effect. Alright, let me repeat. Probably I should go back to the previous one. Do you remember this common source amplifier had a transconductance multiplied by drain resistance? That was the gain. Now we're coming back to the common gate amplifier, where the transconductance is GMB plus GM, which is body effect considered transconductance multiplied by the RD. That's the gain of common gate amplifier. So as I said, the gain is actually the same as common source amplifier. The difference is the polarity will be the same, whereas the common source amplifier you have the opposite polarity. But nevertheless, let me summarize it. For common gate amplifier, the V out is shown over here, the transconductance multiplied by the V input multiplied by RD in parallel with R0 prime 1. But what did I tell you about R0 prime 1? It's very, very high. Why? R0 1 is already very high, but on top of that, you'll be multiplying with the RS multiplied by GM. So it will be even very, very higher. So if you compare the RD in parallel with the very, very high resistance, you only see the RD. That's why the gain will be just GM transconductance in parallel, multiplied by the RD. Then what about these other terms? You can ignore it. In practical sense, you can ignore it. So R out will be RD in parallel with R0 prime 1, which is also RD. Why? Because this is so high. Alright? Are you following up to this case? Alright? And input impedance will be the RS because you're looking from the source side. So just to give you where do you use the common gate amplifier versus the common source amplifier, just to give you an answer, most of the voltage amplifiers you can just go with the common source amplifiers. But for higher frequency response, we'll be talking about frequency response next week onwards. You will have the advantage of the common gate amplifier because do you remember this was done in week 1. This is common source amplifier. There's a small overlapping capacitance. Where does that overlap capacitance come from? From the gate and the source overlap, gate and the drain overlap. And the impedance of the capacitance at very high was what? The very high frequency was Okay, let's also visualize it. Try not to memorize the equation. You pour the water from this side. Can you flow to the other side? At low frequency? No. That means at low frequency, the capacitance resistance is very, very high. So if you have a slow changing signal, the capacitance resistance is so high, you can just consider it as open. But as you start changing the water, let's say you have high vibrating water, that vibration can pass to the other side, and that's exaggerated as the frequency goes up. At very high frequency, it can be regarded as a gain short. So at very high frequency, this capacitance is considered as short. That's a problem. Why? Because you need to have the signal going through this transistor to get amplified, and the phase will be opposite. But as these two points are shorted, input will be directly reflected to the output without any gain. So this is the high frequency response that degrades, the gain degrades. And this happens because there is a direct overlapping pricing capacitance between input to the output, which is not there in the common gain amplifier. From input to the output, there's no direct pricing capacitance. So it means that the common gain amplifier actually exhibits better high frequency response. I'll be talking about that next week. All right? Any questions so far? Okay, you can now understand why I said it's very important to absorb the contents that was covered to this week in order to advance to the next week. So I think this week is actually the, I'll say, plus point. If you don't absorb the content so far covered, you can still recover in the week following, but you will need double the effort. So please do try to absorb all the content we have covered so far. If you have any issues, let's clarify. We fortunately have a tutorial next week. After the tutorial, we'll be having some consultation sessions to you, for you to clarify. All right? Okay. Now you know the drill. We have covered the common gain amplifier with a passive load. What's next? I don't like this resistance. Why? You know this, right? Why? In order to have a higher gain, you need to increase the RD. If you increase the RD, the DC current flowing through the RD increases. I mean, the voltage increases, drops. That lowers the output DC bias. As the DC output point decreases, your swing, along with swing to the bottom, to the downside is reduced. So by having high gain, you will likely have a higher swing. But because of that higher swing, you are now limited how far you can input. Then what's the point of having high gain? How do you avoid this? Now I think you can answer. How do I avoid this? Now we have the problem because of the passive RD. No, it's okay. Let me reiterate the problem. We have an issue, the common gain amplifier as well as common source amplifier and even the common drain amplifiers, that if you have a high gain, you can see that in order to have a high gain, you want to increase the RD. If you increase the RD, with the same 1 milliamp current flowing, voltage drop increases. So instead of half will be VDD, now with the higher current, it will be, let's say, 0.2 times the VDD. Then instead of, let's say, with real numbers, this was biased at 1 volt, then your maximum swing can be with respect to 1 volt, it can go to 2 volt or to 0 volts. Right? You cannot go beyond the VDD or below the ground, so that's the maximum swing. But in order to increase the gain, I increase the RD, which consequently drops the DC biasing point. Now let's say it's only 0.5 volt. But with the increased gain, with the same input amplitude, probably your swing will be something like this now. Because you have increased the RD, the gain is increased, with the same input, you have a higher amplitude. But the problem is, to the lower side, cuts off. So you cannot, this is the swing problem. This happened because you have increased the RD. And we increased the RD because we're going to have higher gain. Right? So this is contradicting. That's the problem we have been exploring. How do we overcome this? Do you remember? How do we overcome this problem? We replace this with what? we replace the RD with what? With the active load. Do you remember we replaced that with the transistor in saturation? Do you remember that? Okay, no problem. Yeah, this is exactly what you have pointed out. So we now, in order to increase the gain, we increase the RD, which consequently reduce the DC bias point, and that's a problem. And this problem happens because the RD is there. What we did was, we actually replaced it. We replaced, instead of a resistance, we replaced the resistor with a transistor bias in saturation. And why is that important? Let me cover that. Because as I said, it's important that we understand what's going on. Okay, so this is the transistor in saturation. If you look at the DC resistance, that is calculated as, let me give you an example, 1 volt, 1 milliamp. DC resistance is calculated as, I think, excuse me, yeah, let's look at it. You have 1 volt and 1 milliamp. So the DC resistance is 1 volt divided by 1 milliamp, which is 1 kilo ohm. That's DC resistance, 1 volt, 1 milliamp. But if you have a swing, this AC signal, like remember that you are going here, you don't feel resistance, but when you try to swing around, you feel higher resistance. That's exactly what's happening here. The AC resistance is the inverse of the slope here, which is it's shown as delta VES or delta VI, ID, which will be typically very high, around 400K, for example. Right? Then this AC resistance is what matters when you calculate the gain. DC resistance is just for biasing to determine where it's starting to swing. Right? How much amplitude you get is relevant to the AC. And how do we get the high AC resistance and low DC resistance? Is by replacing the resistor with a transistor. Right? But this transistor has to be in saturation. And that's what we are doing here. Now we are replacing the RD, the drain resistor, with a transistor in saturation. And how do you make it in saturation? Is by having a current mirror. And this current mirror, you know that the M3 is guaranteed in saturation. How do you know that? Okay, do you remember? This M3 is guaranteed in saturation. How do you know? Yeah, gate and the source. If you look at it, gate voltage is the same as the source, and drain means it's guaranteed in saturation. This was in week 1, right? So then you have the current, that is reference current mirrored to the M2, which is the same as the M1's current, which means M1, M2, and M3 all are in saturation. And this M2 is working as a load. In other words, if I were to ask you what's the gain of this amplifier, the first thing, don't panic. This is not a joke, right? Don't panic. You have 3 transistors, don't panic. You find where the input and outputs are. Input is from the source side. Output is from the drain side. Oh, this is common gate amplifier because gate is common from the input and output. Common gate amplifier means M1, transconductance of M1 is relevant to the gain. And M2 and M3 is not relevant to the gain. I mean, it's not relevant to the transconductance, but it's going to be working as a load or bias. To be more accurate, M2's R02 is working as an active load. And M3 is just biasing M2 into saturation. So, this is what I'm telling you. After today's lecture, you're not going to draw the equivalent AC circuit model. If I were to ask you what's the gain of this amplifier, you quickly identify M1 is the gain element. M1 is responsible for gain because input and output is coupled to the M1. So that means the gain of this amplifier is N1 transconductor, which is GN1, multiplied by the output resistance. And what is the output resistance? R02 in parallel with R0 prime 1. If you can identify it, today's goal is already achieved. By looking into the schematic without any equivalent circuit model, without any equivalent behavior, you already know transconductance N1 multiplied by R02 in parallel with R0 prime 1 is the gain. And we also know that R0 prime 1 is R0 1 of the drain multiplied by transconductance multiplied by Rs, which should be very high compared to the R0 2. So R0 2 in parallel with R0 prime 1 would be just R0 2. The conclusion is the gain of this one is GN1 multiplied by R0 2. To be a little bit more accurate, GN1 plus the back gain of GN1, transconductance of GN1 multiplied by R0 2. Alright? But that is good enough. The accurate gain, you will do the simulation. As a designer, you need to identify, okay, do I need to choose the common source amplifier or common drain amplifier or common gate amplifier? If it is common gate amplifier, what should be the device metric of it? That one, the tool cannot do it for you. You have to do it as a designer. But the accurate gain values, don't try to spend time doing calculations too accurate here because it's not going to be accurate anyway. But as a designer, you're going to identify what type of amplifier you're going to choose. PMOS, NMOS, what type of amplifier? Are you going to use active load or passive load? Then if the case, what should be the dimension, W by L, roughly? Alright, and then run a simulation for tuning. Okay. Nevertheless, let's go to the previous analysis similarly. The gain will be GN1 plus GN1 if you want to be more accurate, in parallel with R02 with R0 prime 1, but R0 prime 1 is so high, it's just equivalent to R02. Alright? Is everyone following up to this point? Yes?
Well, I have two questions. The first one is, what happens if we replace the resistor with two transistors in series?
Two transistor means in series. So for example, how do you mean?
Yeah, replace this one with three transistors.
Like this?
Two transistors. Replace
Oh,
one
two
with-
transistors. You mean two transistors in series? That's what we're going to cover next. So stay tuned. But I like your question. Yes.
So we want to use the common source transistor as a buffer. But what do we want to use the common gate?
That's right. So common source amplifier is the easiest amplifier you can design. Common gate, on the other hand, as I said, I can answer this more accurately at week 9 when we cover the frequency response. But just to give you a short answer, if the high frequency operation is needed, because of this shorting between input and out, common gate is the answer. Right? And there are some cases where we need really high output impedance. A good example is a current amplifier. So far we have been talking about voltage amplifier, but for a current amplifier, you want to have high output impedance because regardless of what load you're attaching, your current has to be constant. Right? In that case, intentionally you need to have high current output, high output impedance instead of what we discussed so far in the voltage case. So in that case, you might want to use the cascade structure with the common gate. So we'll come back to that later. All right. Anyways, to answer your question, what happens if you have a series, two transistors in series, or two transistors on both sides? We'll come back to that. We call it a cascade amplifier. Right? So let's take a look at it. Again, the goal here for today's analysis is to see, without drawing any equation or AC circuit model, what is the rough gain of this amplifier. Okay? So just to give you an answer as a preview, your gain of this cascade structure will be GN1, transconductance of GN1, multiplied by the output impedance seen from drain, which is R03 in parallel with R02 prime. But R02 prime, as you can expect, is fairly high. So you know the story. That's what we're going to do. But anyways, let's do the analysis. How do you know that's the case? If you look carefully, it's a combination of common source amplifier because it's input to the gate, output to the drain. But on top of that, you have this common gate source, because the source is the input and output is the output. You have the cascaded common source followed by a common gate. This is called a cascade amplifier. And there's good reason you're using it. We'll come back to that later. So the bias current in this case will be set by the N1 and the N3. So we first need to make sure if this amplifier is going to be working as an amplifier. What do we need to do? That's right. All three transistors should be in saturation. That's the first condition you have to satisfy. If you don't satisfy that, it's meaningless to do any gain analysis. How do you know that M3, M1, and M2 are in saturation? You need to make sure for MOS case the gate is lower than the drain, or if the gate is higher than the drain, it's no more than the threshold higher. PMOS is the opposite, right? We already learned that. Then imagine you have just three transistors. If you want to solve this by equation, that's going to be tedious process. Please don't do that, but get accustomed to identifying how do you know if this amplifier is saturated or not. Just look at the gate and the drain voltage. For NMOS, if the gate voltage is lower than drain, it's in saturation. If gate is higher than drain, but the difference is no more than the threshold, it's in saturation. Alright, I just write that here. That's simple, but if you write in the equation, this is complex, right? Vx, N1 to be in saturation, Vx has to be low. The Vx voltage has to be higher than the gate voltage. If you write in the equation, Vx has to be higher than the Vin minus Vth1, which is the override voltage. Same goes with the Vx, where the Vx over here, if you look carefully, is the Vb2 minus the Vgs2. Vx is actually Vb minus Vgs2. Makes sense? And Vx, if you plug it in, is Vb minus Vgs2, which has to be higher than the input minus threshold from this relation. If you sanitize it, you can find that the Vb2 has to be higher than this number. That's the Vb here. That voltage has to be higher than that number. Do I need to memorize this? Please do not. It's not going to help. And for U2 to be in saturation, you do the similar analysis. You need to make sure that V out, which is the drain voltage, has to be higher than the gate. That's what I go over here. And that means the V out has to be higher than this, which means the V out has to be higher than the VGS minus VTH1 plus VGS minus VTH2. So just give me a second before I reply. Please do not memorize this, but if you just look at here, in order for these two transistors in saturation, you have to make sure the overdrive voltage of M1 and overdrive voltage of M2 is maintained at this. So what do I mean by overdrive voltage? Overdrive voltage is defined as VGS minus the threshold voltage of M1. That should be typically higher than 50 millivolt to 100 millivolt. To be safe, I'll give around 200 millivolt here. So this voltage has to be at least 200 millivolt. These two has to be also at least 200 millivolt. Combined, probably you need to have a bias point going no lower than 400 millivolt. Then these two will be saturation. Okay. The actual trial region will happen if you have 50 millivolt to 50 millivolt, which is 100 millivolt. But between 400 to 100 millivolt, you will already start seeing some distortion. So I want to get away from here, which means around 200 millivolt and 200 millivolt. 0.4 volt is where you want to have a main design point. Okay, did you understand it? Yes.
Oh no, I just wanted to ask, like, we're finishing this chapter today, I guess. That's all.
Okay. So yeah, we'll come back to refreshing as well. But anyway, that's what I said. Don't try to memorize this. By looking into here, I already know that you need to maintain the overdrive voltage here plus the overdrive voltage here, right? That DC bias point has to be higher than that. Okay, in that case, what's the voltage gain? It's the same as what you have seen here. I will treat these two transistors as a single black box with the transconductance of capital GM. Then capital GM multiplied by the RML3 in pair with whatever the input output impedance you will be seeing is the load that will be multiplied by the capital GM. That's the gain. Right? So how do you do that? Cascode gauge R0 prime and then R03, and transconductance of the cascade stage as the capital Gn. I'll do it for you. That is defined as drain current in M2 divided by the input voltage. That's the transconductance. Voltage gain will be, as I already told you, transconductance multiplied by R03 multiplied with R0 prime 1. Alright? So in this case, we need to find Gn and R0. Those are the unknowns. How do you find it? We did something similar in common drain amplifier. So that black box is the cascade stage, which I'll be replacing that with the AC equivalent circuit, which looks complex, but bear with me. So you have two transistors, you draw all the transconductance, and by the way, for the backgate, for the M2, this voltage is non-zero, but the body is zero. So you do have to consider the body effect in M2. That is considered here. That's why you see the transconductance of backgate transconductance is considered in the transistor 2. And you will set up the equation for the RE2, which you can see here, just you can follow. I already did it for you. And the second equation is from the gauge source, which you'll be setting up here. You substitute 1 to 2, then you will have these really complex equations. I will skip it because I already did it for you. I do the sanitization, I find that Gn is actually Gn1. To be more accurate, it will be Gn plus Gn1, but since M1 has no body effect, you just have Gn1. Okay, I stop here for a moment and let's go back to the previous slide. This Gn of two stages is amazingly the same as the transconductance of M1. Interesting. So these two common source and common gate combined, the transconductance is actually the transconductance of M1. It's not exactly the same, but it's about the same. Alright? And that's enough. Oops, I went too far. And here the assumption is GM2 plus GMB2 is higher than the motor terminal 2, which is typically, and GM2 plus GMB1 multiplied by R01 is also higher than 1, which is always the case, almost always the case. Alright? And what about the voltage gain? Now you know the drill. The voltage gain here is Gm multiplied by R03 in parallel with R0 prime. And that means R0 prime is, you can already guess, it will be fairly high, because if you recall what we did with the common gate amplifier, if there's a source impedance, that source impedance will be multiplied by the transconductance, multiplied by the R01. And that's exactly what's happening here. You have the transconductance multiplied by the R01, multiplied by R02. Because if you look at here, the first transistor M2 has R02. So instead of just looking at the R02, you have something in the R0. Instead of just R02 through here, you will be multiplying whatever you see from this rainboard by the transconductance. That is reflected as a multiplication. And that's what I mean by having this equation. You have the R01, which is equivalent to the source impedance, a source that's connected to the M2. That's R01, multiplied by transconductance of M2, multiplied by the transconductance of the output impedance of the drain port of M2, which you can already see is to be fairly high. Because R02 is already fairly high, but you multiply that by R01, and even further you multiply that by the GM2. Very, very high. Right? And I'm ignoring 1 because for good reason, transconductance multiplied by R01 will be, if you add 1, there's no difference. It's already very high value, alright? So in that sense, your gain over here is now Gn1 multiplied by R03. Why R03 I decide? Because R03 in parallel with very high value will be just R03. Did everyone understand? Let me get back to this schematic. You have this schematic, right? First thing, what do you do? Don't panic. Don't panic. Identify where the input and output are. Input is going to the M1. output is from drain of M2. So this is cascode. This cascode structure means the gain has to do with the transconductance of M1, not M2, just M1. Transconductance multiplied by the output impedance, measured from the output port, which is R03, in parallel with something. And the something will be very high, because this impedance swing from the M1's port will be multiplied by M2's transconductance, multiplied by R02. That will be very high, so just ignore it. Only thing that's seen is R03. So this amplifier gain is minus, because it's cascode is flipping the polarity, minus GM1 multiplied by R03. That's it. What is the output impedance? R03. What's the input impedance? Very high. Yes?
And what's the point of M2?
Right. This is excellent question. Why do we use this? I'll come back to that. This is actually isolating the overlapping capacitance. There's no direct connection from input to the output. The passive capacitance is still here, but this port is not the output port. So the frequency response of this cascode will be much better than that of the common source amplifier. I'll come back to that. And there's another reason. Let me go back to that. That's an excellent point. That's exactly what I wanted to show you here. If you compare the typical common source amplifier versus the cascode amplifier, you can see that in the common source amplifier, the output impedance will be R03 in parallel with R01, around the same order of magnitude. Let's say 200K, around 200K. The output impedance will be 200K in parallel with 200K will be 100K. Whereas here, 200K in parallel with 1 meg, or 2 megahertz, 2 mega ohms, will be roughly 200K. So it's really double the output resistance. And what did I say about the output resistance? Typically, the output resistance in the voltage amplifier should be low, but there are cases where you want to have high output resistance. And on top of that, you can see that the gain is defined as output resistance multiplied by the transconductance. So this will have a higher gain. Cascode will have a higher gain, around twice. Can you see that? All right. Then, okay, let me also ask you, here's what I just mentioned. You have the common source amplifier output impedance will be half of the R03, roughly, because you have similar values in parallel. Whereas the cascode, you only see one. So the gain over here will be higher. Then why don't we just use cascode always? Do you remember the analog echelon we learned in the professor? You gain something, you always lose something. If I tell you that I only gain something, I'm lying. So what do I lose here? Yes?
Use another transistor.
That's obvious problem, yes. Voltage swing, yes, in terms of the maximum swing, you now have to identify two overdrive voltage versus one, yes, reduce voltage swing. Any other things? Tradition. Right, this is, thank you. When the VDD was 3 volt, not a big problem. But now the VDD these days is 1.1 volt. After subtracting 200 millivolt here, 200 millivolt here, 200 millivolt here, which already is 600 millivolt, the available swing is now 500 millivolt. Whereas here, you only have 2 override voltage to deal with. You still have 700 millivolt. So the more transistors you stack in series, the less headroom, we call it headroom, how much you can play with in terms of swing, is reduced. So if your output swing is not a big concern, you may as well go for a cascode. But if your output swing is a concern, you might have to carefully adopt this, because there's a series connection of transistors. Right? We saw that. Do you understand? So? Really? Okay. That's good. Compared to the common source, cascode amplifier has some forward transconductance, but higher output resistance. Therefore, cascode amplifier has higher voltage gain. Higher voltage gain because of the load, which is higher. With the penalty headroom. Okay, can you guess what I'll be doing next? Yes, but yeah, sure, yes.
Current source.
Before current source, there's one more thing. It's relevant to your question. You asked, what happens if you have series connected in the load? That's exactly what we're going to look at. Right? I'll come back to the simulation. How do you further increase the voltage gain? Now you have two test code loads. Can you guess what happens here? Yes?
RO increases.
It increases. Can you guess why that's the case? It's exactly the same as RO prime increases with the presence of the source attached. If you look at here, previously without M4, the resistance seen from here is R03. Now you have something else additionally attached. That resistance seen from here will be R03 multiplied by transconductance on M3 multiplied by whatever you see before, which is R04. So effectively, it is R0 in the order of R0 R0 squared. That's the effective resistance. That, of course, boosts up the gain significantly. Okay, so you have increased the gain significantly, but what do you lose? Voltage swing is even further reduced. Why? Now we have to identify 200 millivolt, 200 millivolt, 200 millivolt, 200 millivolt. If the supply is 1.1, you now only have 300 millivolts. That would be very, very small overhead. So in that case, you may as well increase the supply by switching the transistor to a higher threshold voltage. That's another reason why analog designers don't use the most advanced process node. Even to date, right now your mobile phones, let's say for example M3, A14 processors. If you look at the analog amplifier inside, we don't use the most advanced process node because it doesn't give you advantage at all. It actually gives you some penalty. So how do you deal with it? Typically you use the higher I/O device, higher threshold I/O device to play with higher supply voltage. But nevertheless, that's about it. This is what I was going to say. Higher gain, reduce voltage swing. Let's look at it for a moment. Now the R0 prime prime, which as you can expect, it's M3 multiplied by the resistance seen from the green, which is R01, multiplied by R03. You can probably now guess that. That will be in parallel with R0 prime, which is GM2 multiplied by R01 multiplied by R02. Those two will be divided, in parallel. That's the resistance value seen from the output. The gain will be half of that, because you have similar values to right and left. That's what you're going to see. As you can see, compared with the single stage, you see now two transconductance of M1 and M3 are multiplied, and two output resistance are multiplied. That's extremely high. Right? Output resistance value will be R01 multiplied by R02, which is dividing GM3, R04, R04, R03. That's roughly the case. Right? So whenever you see this, again, don't panic. Just sit there and see where they put an output chart. Identify which transconductance matters. In this particular case, M1's transconductance is relevant to the gain. You can already see that. And then where is the M3 and M4? That's because the load has the multiplication of M3 transconductance. But the amplifying transistor is only GM1. And that's what you can get from here. So it has extremely high gain with a penalty in the output swing. So if you have a supply voltage fairly high, probably that small overhead is not a problem. Right? So that's where you have to, as a designer, properly choose the design. So for example, what is the maximum output swing? Without even do any analysis, you already know the answer. The available swing to the plus is VDD minus the overdrive voltage of M4 minus M3 overdrive voltage. The lowest you can go to is that you have the overdrive voltage of M2 plus the overdrive voltage of M1. Because below that, these transistors will start going to a trial region. Okay? Yes?
Instead of having two transistors in series, couldn't we just make one transistor longer?
Yeah, that's also a good question. If you make it one transistor longer, now it's not actually longer, it's wider. It'll have similar characteristic in terms of, let's say, the drivability. But the problem is you will not be enjoying this isolation of high frequency response and etc. So it's actually different. Yeah. So in order to achieve this higher resistance, you actually have to do the cascade structure at the penalty of the overdrive voltage. Now let's look at the maximum swing. By looking into this and VDD minus the overdrive voltage minus M3 is easy to understand. That's what's needed. If you put it in the equation, it looks so complex, right? Swing plus is half of VDD minus V top, which is half of VDD minus V top, and that means half of VDD minus the overdrive voltage, which is 2.5. All right? V minus, swing minus, is half of VDD, which is the output bias point, minus the bottom. This bottom are the combination of two overdrive voltages. And the swing is minimum of these two, whatever is smaller, multiplied by 2. Alright? Does that make sense? Okay. Now, advantages and disadvantages of cascode is advantage, higher voltage gain, very high output resistance. This is typically a penalty for voltage amplifier, but for current amplifier, this is something required. Common source and common gate stages in cascode use the same bias current. We call it current reuse. If you have two-stage amplifiers, each transistor needs bias current. If you stack them up, you get higher gain without using more additional bias current. That's why we call it current reuse. Right? High bandwidth. I already give you some preview of that. Since the Miller capacitance of current source stage is not shown, I'll be coming back to that next week onwards. But if you gain something, you always lose something. This is the same when you do the research, you read a paper. If a paper says you achieve many good things, then you should turn on your switch. Something's fishy here. Something that these people didn't talk about, right? So this is something, this is ground truth. So disadvantage here, limited output swing due to 4 transistors stacked. Okay, that gives VDD minus 4 overdrive voltage transistors. Seriously reduces the output swing to play with. And not suitable to drive the resistive load. Can anyone tell me what this means? I already spent some time at the beginning of today's lecture. This is not suitable to drive resistive load. This cascode stage in the bottom as well as cascode in the load has extremely high output impedance. Very high. If you're driving the resistive load, with that extreme high gain, it's all lost by the voltage division. So if you're driving the voltage load, low load, impedance load, this is not suitable. How do you solve this? Yes, insert a voltage buffer. If you don't like inserting a buffer, just go for other type of amplifier. That's another way to go. Alright? But anyway, I think I'm happy that most of you got it correctly. Now I'll get back to, before I finish today's lecture, I'll get back to the simulation. Design a single stage cascode amplifier with a 0.18 process CMOS with the aid of cadence or the following specifications. Now the voltage gain is 80. If you know this, the lecture I designed is structured in a way, the first example had the gain of 20. Remember that? And the second example had the gain of 40. Now the gain is 80. There's good reason for it, because with the same amplifying transistor, we have these different topologies that aids higher gain. But of course, you now know that if you have a higher gain, something is lost. And here the swing is lost. Anyways, now given the supply 1.8, the drain current is, bias current is 250 microamps. Threshold voltage of NMOS is 320 millivolt, PMOS is 450. Oh, I got a question from one of you. Sorry, I don't remember the name yet. How do you set the threshold voltage of an NMOS in cadence? That was the question. The answer is threshold voltage is not something that you are setting. it's actually once you have the transistor defined with W over L, it is already given to you. Right? That's a physical metric that is already given from a division of transistor. Then why do I give the threshold voltage of 0.32 here? Is because depending on the dimension, roughly the threshold voltage of MMOS will be 315 millivolt to around, I'll say, 400 millivolt in that ballpark. PMOS will be something similar, but for this particular example, I'll just give you this threshold voltage. Alright? But it's not a fixed value. Depending on how the length and the width of the transistor is, the threshold voltage actually changes. And we already know, as the body bias changes, the threshold voltage also changes. That's why you cannot set a specific threshold voltage. Alright? Anyways, with all this metric given, sign it. I have calculated how do I start? I start by giving bias curve over here, then will give you the override voltage with the W over L. So I set the override voltage to be, let's say, 200 millivolt, whatever it is. That gives the voltage over here. That gives you the VDS. That also gives you the threshold voltage is already given. Then you can set the W over L to what you need. And I just made the hand calculation. This is what I got. So I have 20 micron length and width, and then 300 micron length. Same here, 20 micron and 300, 11 micron and 300. And I had to set this bias point, VDC to be 1.1, VDC to be 1.2, and VDC to be 600. Alright? And then I got a nice gain of 82, but the swing is much more reduced. If you compare with the 3.3 example, where the swing was, 3.2, where the swing was very high, now I have a reduced swing. Higher gain but reduced swing, right? So the message I want to give you today is, let's try to clarify and do the simulation up to example 3.2 by this week, all right? But no longer than, let's say, mid next week. You will finish that, and then you are finish the sub-project number 1 as well. I mean, you don't have to do it before the deadline, but try doing it. And if you have trouble with the simulation, please let me know beforehand. Yes, are you asking some questions? Oh, okay, yeah. And if you have trouble with the content, if you have some doubts about the content you have covered, please send an email to me, and also copy TAs and GAs. I really request you to copy GAs in all the emails because I sometimes fly out for a business trip and I become unresponsive. If I'm on the flight, I can't reply. But if it's urgent, the GAs can help you as well. So please add the GAs in the loop. And the simulation, thank you for letting me know that the workshop is not open. The PIQ is not open over the weekend. I'll check that.
It's open, but it's not like open like same as Monday to Friday.
So you have to key in the pad, right?
Oh, you have to do that all the time actually.
Okay, so let me double check that if they can allow access. Okay, anyway, that actually ends the 2 weeks of journey regarding the single stage amplifier. This table is for you to fill in. You don't have to. But again, what's the goal of lecture up to this point? Is that you have an unknown schematic shown up. You will not panic. You will not panic, and you will identify where the input and output is, and you start from there. You start from there, you identify what type of amplifier this is, and you have to identify what is the condition for these transistors to be in saturation. Right? And then you will be probably calculating the gain, setting the gain as you want, etc. Alright? Any questions so far? Yes?
Will you do a live demo of one of the examples, like a simulation on a cable?
Okay, we can try doing that. Let me set it up with a GA for that session. We can probably do it in week 6. If not, yeah, let's see if we can do that. But I can also give you one thing. Okay, I forgot to mention something. Next week tutorial, the question is already unloaded. Has been unloaded since week 1, right? I mean, from week 0. But anyway, I really beg you. At least the good thing is that if you can solve all the tutorial questions before you come in, that's the best, right? But if you really don't have time, try at least one question yourself. Why? Because if you come to the tutorial session and you see me solving this, it looks like, yeah, it makes sense. Yeah. But if you haven't tried it yourself, I can tell you it will not be as easy as you might think. But once you do it yourself, and then you will become a custom tutor, it'll be very easy, right? So please solve at least one question before you come to the tutorial next week. It's in the same venue, Thursday, 5 p.m. Or is it 4 p.m.? 5 p.m. Okay, any questions? Yes.
Can I ask for one gate amplifier when you replace the passive load with the active load? Why do you use a current source instead of a common PMOS?
You can use a common PMOS, but okay, that's a good question. If I had more time, probably I would start off with just one PMOS with the DC current, DC biasing. But I already told you that was not preferred because you now need to have two separate DC sources. So that's why I prefer using a current source and with the current mirror like this. So then you don't have to you can get rid of the voltage independent voltage source. If you use just PMOS as active load, you need to have a separate bias DC, which has to come from somewhere, right? So somewhere is actually adding a voltage DC-DC converter with the voltage regulator, which is not preferred. You want to reduce the number of voltage regulators on chip. So technically speaking, it's possible, but the same reason we introduced this current mirror as an active load in the first place, the goal was to reduce the number of DC sources. That's the answer. Yes.
Alright, for the active flow, if you want have like a lot of active flow. And
You have a lot of
first you say because you don't want to use DC source, you want to use a current source.
right. I already covered this, but let me repeat that. The current source, typically when you implement this type of it, is nothing but one resistor. Why? You don't want to use the resistor as a load because I already mentioned to you there's a trade-off between the output swing and the gain, right? But here the reference is nothing but a resistor, and this is DC resistor. It doesn't function as AC. So here it's totally okay to use a resistor, and typically current source is replaced with a resistor, and that's what you're going to do in sub-project 3. Sub-project 1 and 2, you are allowed to use a DC source. Sub-project number 3, except for the input bias and the supply, you cannot use other bias circuit. You have to generate all the bias yourself, meaning that you will probably need to use this current mirror and the active load. Yes.
If you want to ask is where you want to connect a lot of active, how do you connect a lot of active load to this car?
That's right. Do you remember when you talked about curve mirror, you can have another branch? Like this. As far as you take the gate voltage from the M3, which is direct connection, and then you have another branch, you can have multiple branch from the same current. But you may not necessarily have the same current. You can just adjust the ratio of WL and WL here to adjust the amount of current that you need. As you remember, if you have the same WL from these two branches, the current is copied. But if you have the WL of 10 here and WL of 20, then you have twice the current going here. So you can just adjust the WL from the branches to the needed bias current. Alright? If you already use this for subproject number 1, that would be excellent. Because you'll be needing it anyway for subproject 3. But the disclaimer here is that for subproject number 1, you don't need to have the current mirror as a current source, the biasing. You can just use a separate DC source. Right? Any questions? I will end the lecture here, please. Oh yes.
My question is about
Let me stop
example
it.
3.2. So
Sorry?
my question is about example 3.2.
3.2, okay. Let's get back to that. Yeah.
So actually, because when I calculate the time, right, I somehow got a VOD of 0.625, which I'm not sure why.
You got VOD of 0.6.
6, yeah. But
Okay.
I know VOD is supposed to be 150 MV to 100, right? Yeah. So
Yeah, so the overdrive voltage of 200 millivolt I mentioned is not a fixed value. Of course, it makes sense because the overdrive voltage by context is VGS minus VTH. If you have a higher GS, of course the overdrive voltage is higher. But that gives you more margin. So the overdrive voltage of 200 millivolt is the minimum overdrive voltage you have to guarantee. So if you make it 600, that's even better. Because now you have allowed swing of around 400 millivolt to go there. If you just have overdrive voltage 200 volt and that's it, that's millivolt and that's it, then your design margin is very narrow. You got it? Okay. So for example, if you have design the amplifier that reaches to 200 millivolt at minimum, then if it goes below, let's say 200 millivolt, let's say 100 millivolt, then it's dangerously close to getting this to try release. But you design on the contrary, you design an amplifier that the output swing only goes to 600 millivolt. Then it's well above the overdrive minimum overdrive voltage required. So in that context, it's a good design because make sure that your output swing doesn't affect the saturation of this amplifier. So you don't have to go for 200 millivolt. Anything above that is good.
Yeah, I understand. But is it possible you look through my workings?
Sorry?
Is it possible you look through my workings?
You mean example 3.2?
Yeah.
Yeah, 3.2 I can, but if you ask me to go through subproject number 1,
No,
that's not fair. Yeah, so you can go. You can go ahead and that's right.
Okay.